Hello and welcome to ECE 252, Systems Programming and Concurrency. I'm Jeff Zarnett, and I invite you to watch the introduction in which I talk a little bit about myself and tell you about the course and its calendar description and that sort of thing. But if you've decided to just jump right into the lectures, then, well, here we are. For the most part, you're not going to be looking at me because this course is done partly with some slides and partly with some demonstrations where I'm going to have a code editor open or a terminal. We're going to run some code and look at some output and just generally get into the details of what we're doing. So you're not going to spend the same amount of time looking at me as you would if we had our usual lecture hours in the course. In any case, you may notice that there are only about 30 topics. However, the length of the course is your standard 36 lecture hours. And some of the topics will go on a little bit longer and some of them will be a little bit shorter, but in the end, we will get to where they need to be. With that in mind, I don't want to spend too much time on the long, unnecessary, skippable intro, just as there's no clickbait thumbnail, and I will not be asking you to like and subscribe, and there will be no ads for terrible mobile games with bad segues. I just want to get a little bit of that out of the way, and if you just decided to jump into Lecture 1, you could have some idea of who I am before we actually get started. So thanks for that, and let's go. This is Lecture 1, Introduction and our C Toolkit. As our first order of business, we would normally go over the course syllabus. This is something I invite you to actually read about in Learn as opposed to me going over it on this version. There is, of course, a distinct possibility that these lectures are being viewed not during the current term in which they're being recorded, so any syllabus information that I tell you now could be a little bit out of date. Nevertheless, whatever term you're viewing this in, you should be reviewing it just to make sure to not miss any important details, including things like the grading scheme, contact information for the course staff, course policies, and university policies. Okay, another thing that's noteworthy is that the source material for the notes and slides is open source via GitHub, so if you find an error in the notes or the slides, or if you have an improvement, then please feel free to go to the GitHub link here and correct that. If you can open an issue, I can address it. Even better, if you are familiar with Git and with LaTeX, then you can go to this URL and you can submit a pull request for me to look at and to incorporate. And doing so helps make the course a little bit better for the class that follows you. Okay, so I need to start by giving you a little bit of background information about the material. And we're going to start by thinking about the operating system. So an operating system, frequently abbreviated OS, is a piece of software that sits between the hardware of a computer and the applications, also known as programs, that run on that computer. The operating system does many different things and often has many goals, some of which may conflict with one another. If you wanted an analogy, you could think of the operating system as being the secretary or assistant of the computer. It's a resource manager, so it allocates resources as necessary. And the thing about it is that unlike having a person who is your assistant, who you can assign work to, and they do work while you are doing something else, every time that the operating system is running, that's time when other programs are not. And that means the operating system, runs when it can and when it has to, but it tries to do so very efficiently because ultimately what you want when you are running a program is for your program to run efficiently and to run quickly, and not for the operating system to spend lots of time doing its own thing. If you are playing a game, for example, you want the game to have the highest performance possible. You don't want lots of time being spent on the operating system's upkeep tasks. Now, the operating system has a lot of responsibility in this. It sees to it that programs can operate efficiently and that they can get the resources that they need. And the operating system is responsible for resource management and allocation because it's one of those things that it could be done wrong if it's not well managed. Resources like CPU time or memory space are limited. Even if you have a tremendous amount of memory and you're not worried about running out overall, there is no way that you can have two processes using the exact same space and memory unless that's intentional. There's got to be some sort of management of this. So the operating system has to decide how to allocate resources. That requires also keeping track of system resources and cleaning them up when they're no longer needed. And in the event of conflicting requests, making a determination about what gets to happen next. For some devices, that will be simple. That will be first come, first serve. If you want to print a document, well, whoever prints the document first, their document is printed first, and that will do. For other things like the CPU, you might say that doesn't make sense and that higher priority things should get to go first, even if they didn't wait in line. So there will be frequently conflicting requests, and the operating system has to choose the winner. Now, the goal for the operating system, as I've said, is to help useful programs like Photoshop or Microsoft Word to run. And it is the responsibility of the operating system to make this not only possible, but also to make them portable. That is to say that when you want to run Microsoft Word, it's not super important what the exact details of the hardware in your computer are. How many gigabytes of RAM do I have? What CPU exactly? What is the screen resolution of the monitor? Word doesn't have to be written so that it is capable of handling all of those tiny differences and sometimes large differences between different computers' hardware. What happens instead is the operating system abstracts away those details, making it possible for you to write your program and just ask the operating system for what you need. You can imagine, if you would, that Hello World would be a very difficult program to write if you had to write it differently for every different hardware configuration. There are so many possible variations out there, there is no way that you could anticipate them all, and why should you have to when the operating system can do that for you? And in most cases, there are multiple programs that are running at a time, and some resources are shared, which, as you may imagine, is potentially a source of conflicts. And well, the operating system has to enforce rules so that everybody can get along, so at least the world is somewhat fair. Sometimes also processes want to cooperate rather than compete, and the operating system can help them do that as well. And the operating system is the backdrop. It is the stage, it is the helper to a lot of what we are going to do in this course, and that is systems programming. Now, systems programming is the next layer above the operating system itself. There are certain tools that sometimes ship with the operating system, but they're not really part of the operating system itself that we would tend to rely upon. But what distinguishes systems programming from just general programming is how we are calling the operating system and asking it to do things for us. So some examples of things like system programming are file manipulation, a program that creates, deletes, copies, renames, prints, manipulates files in some way. This is systems programming. Communication, remote login capability, file transfer, download utilities, messaging, all of those things. Process and thread management, so creating processes and threads, working with them, interacting with others, cleaning them up. If those terms about processes and threads aren't familiar with you yet, don't worry, they will be in just a few lectures. Now, writing systems programs is more difficult than writing just a general purpose program. It might require you to know at least a little bit about the hardware, maybe not exact details, but about the kind of device that we're looking at or about its limitations. Perhaps programming facilities like debugging are somewhat limited. It can be difficult to get insight into your program when your program invokes some functionality of the operating system and you can't really see what the operating system does because for security reasons you're not told what that is. And moreover, concurrency starts to become a problem when we start to think about systems programming at this level. And concurrency is the other big topic in this course that we're going to spend lots and lots and lots of time on. Now, when we talk about concurrency, we are limited a bit. A simple program may be able to forbid you from having two windows open. You want to have two email windows open, and the email program says, no, I'm sorry, only one is allowed at a time. That's fine, but when we think about what does the operating system do, you could not limit it to say only one file operation can be in progress at a time. Users would not accept that. And the key thing is that distinguishes systems programming from just general purpose programming is how much we will ask the operating system to do things for us. There are things that the operating system does not allow programs to do, and we'll talk about what that's about and why shortly. And there is a system by which we invoke the operating system and ask it to do what we need it to do, and then collect results. And for any non-trivial program, it is very likely that we will at least interact with the operating system some of the time. Okay, so the previous section mentioned concurrency, but it didn't really introduce what it is. A program is said to be concurrent if it can support two or more actions in progress at the same time. That's not the same thing as parallel. Parallel is two or more actions executing simultaneously. So to illustrate the difference, suppose you have an assignment in course A and an assignment in course B. If you start the assignment for course A and you get 20% of the way through and you decide I'm going to put this down for now and I'm going to switch to the assignment from course B, then we would say that both of them are in progress concurrently. There is some progress on A and there is some progress on B. That's distinct from the idea that you would finish A completely before you pick up B. You are only working on one at a time, but you have two assignments in progress right now. It is parallel if these two things are happening at the exact same time. So if right at this very moment you are working on the assignment for course A and your friend is working on an assignment for course C, if you pause time at 8:37 a.m. on this day, person 1 is working on this assignment and person B is working on that assignment, then that we would say is parallel. And in the computer context, it's the same. You could have a task that's in progress and the CPU is working on it, but it puts it down for now and comes back to it and starts on something else in the meantime. And we would say that is concurrent. Whereas if we stopped the CPU and examined what it was doing, if there were two things that were executing at the exact same instant, that would be parallel. We will spend a great deal of time examining the differences between parallelism and concurrency when we get to that topic in the course. Now, it is to a greater or lesser extent already the case that many of the programs that you already use are somewhat concurrent. Depending on your level of programming experience, you may have already written a concurrent program, either intentionally or without knowing it. If you've ever written something like an Android application where you do some background tasks, contacting over the network, a background task is an example of concurrency in your program. If you have somewhat less experience, then the model is something like ECE 150, Introduction to Programming. Everything is sequential, in which case this is somewhat new. We're going to learn about concurrency as a topic. We're going to learn about how you take a program and make it concurrent, as well as how to write with concurrency in mind from the beginning. Sometimes that latter option is best because there will be inevitably some problems when converting it from sequential to concurrent, and they may be easily solved or they may be difficult to solve. So, the drawback to concurrency, though it has many advantages, chief among them that you can get your program done a lot faster. That is to say, you can speed up something, reduce the amount of time that it takes to get an answer, but it comes with drawbacks. On top of being somewhat more difficult to write, that is to say, that we have to write more code and we have to write different code and sometimes harder to read code to make that happen, but it gives the risk of a concurrency problem. And if you consider a program that performs a simple calculation given some input, if the program in question has a concurrency problem of some sort, then the answer could be either 1, consistently the wrong answer every single time, 2, different on consecutive runs with the same input, or 3, correct some of the time, but incorrect some of the time. If you bought a calculator, handheld one, the kind that math would be comfortable putting a pink tie on, and it only gave you the correct answer 99% of the time, would you be satisfied with your purchase? I think the answer to that is most likely no. I think you would say this is defective and I don't want it. I want to get my money back so I can buy a better calculator that doesn't have this problem. And yet, software, admittedly it is more complex than the typical calculator that you can just buy in a shop, is frequently wrong. It frequently has concurrency problems where we do get wrong answers sometimes, or we get the wrong answer every time. And that's not good. That's not good. Without going into the statistics, if your company's payroll system only got it right 98% of the time, then if the company paid you every 2 weeks, that is 26 pay periods per year, then statistically, they would be likely to fail to pay you at least once within your first 2 years working there. So correctness matters. You do not want to miss a paycheck as a result of a software problem, even if you got it 98% right. That's unpleasant. Okay. So you know a bit about the what of the course. You've hopefully read over the syllabus and the calendar description and all of that by this time, and I've told you a brief introduction to the idea of systems programming, and I've given you some hints about where we're going to go with concurrency. But what about why? This is a mandatory course for computer engineering students, which is probably most people who are watching this video. That's fine, but what will you get from it? And here's my thesis for what you'll get out of this, stealing the title from a book, Good to Great. The purpose of this course is to give you the tools and skills to be not just good, but great. What does it mean to be great? Well, good programmers implement a feature efficiently. Great programmers improve the program architecture to solve a whole class of problems at once. Good programmers can use a network communication library. Great programmers can write that library. Good programmers can find their answers to questions on Stack Overflow. Great programmers can write those answers. And past students will confirm that employers ask interview questions about topics in this course. They want to know if you know the difference between threads and processes, if you understand how a producer-consumer architecture works, if you've ever used a mutex. They care about those kinds of things, and if you can speak intelligently about that, then it will be only to your advantage. And if you master these kinds of topics, it opens all kinds of doors for you in the workplace. I'm guessing you probably don't want to be a junior or intermediate developer your entire career. I mean, obviously you will start as a more junior person and you build up experience, but do you want to get there quickly? Whether you choose to advance your career down the individual contributor track or technical lead/management track, you need these knowledge, you need these skills. You will be able to solve problems that other people can't solve. You will be able to see solutions that other people don't see. You want that. It will only help your career. And you do want to be great, don't you? I mean, of course you do. You want to be the very best, like no one ever was. Okay, but I have to be honest with you. This course is going to be hard. This will not be easy. There will be a lot of work. It will not be a cakewalk. If you don't feel confident in your programming skills, now is the time. you should, at the beginning of term, invest as much time as you can in catching up on things that you missed. We're going to spend some time later on talking about C as a programming language, so you can get an idea of, here is a quick catch-up guide if you don't really feel comfortable with C as a language. It's intended, of course, for people who have experience with C++, but if you are not feeling great about that either, then you should spend even more time working on the programming stuff. So yeah, this course is going to be hard, and I want you to take it seriously. For our next topic, we will do a somewhat lengthy introduction to the conventions and the tools of C as a programming language. And I'm going to split that off into its own video just so you can look at that separately, sort of anytime you want to catch up, review, anything like that. But there are a lot of tools and conventions that we should actually talk about, and it's nice that we can demonstrate them. Now, there is a baseline assumption, again, that you have experience with a C-like language, and this is going to only help you if you have previous experience in C. You might also consider, if you want to catch up on some C stuff, that there exist tools on the internet where you can sign up and do programming problems using the language. That's an additional opportunity to practice C if you are so inclined. Okay, we'll end it here, and in the next topic we will talk about C.